Lecture 6.3, Interpretation of the Drift Speed. From example 6.1, a current of 1.67 amps in a copper wire has a drift speed of 0.15 millimeters per second. What is the physical significance of such a low speed? We should think about an analogy in order to do that. So picture-wise, let's think about an outlet. Let's say that we have an outlet right here, and it has two plugs. Right, there's the verticals, and then there's a dot, and then over here we have a lamp. So if I'm thinking about this lamp, I could imagine that I have a lamp that looks something like this. So if I have this lamp, it has to have a plug that has to plug into the outlet. So I could imagine that we are running the plug, and what we're going to say here is that the distance from here to there is 1 meter. So I'm looking at this plug here, and it's doing this here. And then we finally turn on the light because we've now attached it here to the outlet. And so we know that there's going to be current flow that's going to go through the lamp. So in essence, if we treat this as not AC but DC, then that means here that I'm going to have current that's coming in, and then I'm going to have a line that's coming back. So current is coming in, current is coming out. So now what we want to think about is that many people say current comes out of the outlet, travels along the wires, and finally reaches the lamp's light bulb. Right? So the outlet spews out current, charge. The charge goes along the wire. It then goes in and it lights up the bulb. Now we want to check here, does that make reasonable sense? Now that we've calculated VD is equal to 0.15 millimeters per second, how long will a charge from the outlet reach the lamp? Well, that's just a simple kinematics relationship where we just say if the drift velocity is constant, then it's going to travel a distance of 1 meter over a time. And so then this time should then be the distance divided by the drift velocity, which will then be, of course, 0.15 times 10 to the minus 3 meters per second into 1 meter. And that turns out to be 1 hour and 50 minutes for that time. And you got to admit, this is a really long time. If you're of the mindset that this is exactly how charge current behaves, then you're going to be waiting a really long time. Furthermore, you got a really big problem in explaining why the light turns on almost instantly. So if you believe the charge coming out of the outlet is what turns on the light, you have a really big problem of explaining why the light turned on almost instantly. In other words, what gives? My response is you have a misconception. With current flow. And so what we need to do is that we need to start thinking about a different way. The fact is charges are already everywhere. That means in the wires and in the light bulb. When the light switch is turned on, an electric potential incline is set up at almost the speed of light. For intensive purposes, we'll say that it's instantaneous, even though it's not. The electrons already in the light bulb immediately begin to move, and the light turns on. The electrons coming from the outlet will take 2 hours to get to the already turned on light bulb. So to try to get an image of this, I want to use an applet which I really like. It's Phys circuit applet. And it actually shows this image that I'm talking about. And so what we want to do is change and go to this applet. So what you're seeing here is that I have a battery, and it turns out that I turned the battery around. So it turns out that the gold is the positive, the black is the negative. Electrons come out of the negative. So this is a little bit skewed, but it's still the same process. So now what you want to pay attention is that look at the wires, look at the battery, and look at the light bulb. Those little blue things are already the electrons. They are already there. So now if I start to make a connection, as soon as I make the connection, look what happens. The charges in the light bulb are starting to move. But these charges take 2 hours to get from the outlet to the light bulb. So this is what I mean by charges already being there. So if I now go and I share something differently, here's my image here. Okay, I just took a screenshot. And so when you look at the screenshot, here's what we're looking at. The charges that are moving here, right? They're moving at the drift speed of about 1/10 of a millimeter per second. So if I was to look at this specific charge, this charge takes 2 hours to reach the light bulb. 2 hours. So that means to go from here to get to, let's say, right here, that's the 2-meter distance. That means to go from here to there, to go from point A to point B, that's what happens. So what you're also seeing here is that look in the light bulb right here. In the light bulb, there are already electrons there. So that's why the light turns on instantly. That's why the light turns on instantly. There are plenty of electrons around. Now, I want to go back and I want to look at a more detailed example. And I want to look at the physics of a jump start. Now, I'm going to assume you know what a jump start is a little bit, but not too much. And so the idea of this example, it's to drive this concept of the drift speed being so slow that a different mechanism must occur. Because a lot of times people believe that charge spews out of the outlet, goes along the wire, and then suddenly the light turns on. But if you did that, you'd be waiting 2 hours. So here we will look at the physics of a jump start. So I would say that a jump start is a procedure of starting a motor vehicle or a car or a truck or whatever you want to talk about that has had its battery discharged. So again, there's misconceptions. So what I'd like to do is I'd like to try to deal with a couple of the misconceptions here. And I would say here's a good one to start with. For starters, there are no 12-volt batteries. Even though we say 12 volts, it's not 12 volts. The vast majority of car batteries, so I'm going to say that most car batteries have 6 cells, and we'll go at this later when we talk about power supplies. They have 6 cells at 2.1 volts per cell, making the car battery 12.6 volts, not 12 volts. So a car battery is 12 volts. Now, what we say here is that this is the nominal value, which implies here that on average, the car battery is 12.6 volts with some small fluctuations. So for example, if your car battery was to discharge to 12 volts or below, man, your battery's toast. You have a dead battery. And yes, I meant to write dead twice because if we say we're going to jumpstart, people say, well, I have a dead battery. That means that you probably can recharge it. But if it falls below 12 volts, you got a dead battery. And a dead battery implies here, so if you have a dead battery, no amount of recharging will bring it back. By the way, as an aside, you may realize that people talk about turning on the car in order to do a jump start. Well, the reason why is that when your car is running, its voltage increases to around 13.8 volts to 14.2 volts. Okay, so that's a misconception right there. So now let's go to where I really want to be. Now I'm going to imagine that we have two cars. Okay, so suppose a blue car has a dead battery. Not a dead, but a dead battery at 12.3 volts. This means it's around 60% of its full charge value of 12.6 volts. So just as a figure that we could think about, I actually know these numbers. So imagine that we have, let's say, let's set up a table. So this is here. I don't know how many values we should go to. Maybe we'll just go to 4 values. I have these values memorized because my father was a diesel mechanic. Actually, that's not 4 values, that's 3. So when I look at these, this is what I'm seeing. I'm seeing that these are going to be my values, and we're going to deal in percentage. And then up here, we're going to talk about the title of this thing, and we'll say that this is the voltage charge, and we're going to be talking about it in percent values. So the way I always remember it is that I think about even numbers, and it goes like this. I know that this is 100% fully charged. If you get to 12 volts, you're at 25%. That's a big deal. So it's not a linear thing, but I do remember that this is 50% and this is 75%. So these are just numbers that are in my head. So what I'm saying is that if I have a battery that's at 2.3 volts, it's going to be somewhere around 60%, roughly. So now what's going to happen here, okay, so now that I've talked about sort of like this voltage chart, I'm going to say that this blue car needs a jump start. So an orange car with a good battery, and that means that it's fully charged when not turned on, comes by to help by giving a jump start to the blue car. So what happens here is that one connects the two positive red posts with the same cable, and it's repeated with the with the black posts, the black negative posts. So let's draw a picture of this. I don't know how this is going to come out, but you could imagine that we're doing a top view of this. So I'm going to imagine that here's a car, and I'm going to try to draw a car and just say, and so if this is my blue car here, you could imagine that I'm going to have some windshield here. And of course, we have side mirrors. And so if this is the blue one, we'll just color this guy out. Now, what we'll look at here is that we need to put in a battery. So we'll say here is that this is a battery right here. And this battery has two posts. It has a positive post, and it has a negative post. So we're saying that this is the bad battery, which has 12.3 volts. It's just over 50% discharged. So if I talk about, I mean, color's arbitrary. I could have picked a purple car, but let's say that I now have the same type of thing here where now I have my orange car. And again, similar situation. We draw the windshield. And so when I'm looking at this car, we know that the battery is also right here in front. And so that means I have a positive post and I have a negative post as well. So then the idea here is that you take the red cable and you connect the two red posts. You take the black cable and you connect two black posts. And in this situation, this is the good battery. And this guy's equal to 12.6 volts. But we don't want it to be at 12.6 volts. So what do we do here? What we do here is that they ask you to turn on the car. That increases the voltage to 13.8, to 14.2 volts. And even if you rev it up, you bring in the alternator, which even kicks that even higher. But that's the reason why you want to turn on the car so you can get that higher voltage. Now, another thing that you may not realize is that this is just an aside. The black negative post is attached to the car's chassis. I think chassis has two S's there. And what that really means, it's attached to the metal frame. And it turns out that this is the car's ground. So you don't even have to attach it to the black post. One can also bypass attaching to the black post and connect, let's say connect, you just got attached to the chassis, connect it to the bumper, for example. That may be more convenient. Okay. So now let's start looking at this. So the goal here is not to get into the technical issues of a jump start. We might in the next chapter, but not in this chapter. But here are some facts to remember. One, as the wording suggests, a jump start is supposed to start the blue car, the blue car's motor. To do so, the good orange battery must start the blue car's starter. So the starter is what turns on the car. Two, once the blue car has been started, then the car has a system in place to charge up the bad battery. And I would say this is a misconception. The good orange battery does not charge up the bad battery. It does not charge up the battery. So now let's get into the physics here. So I would say that this is the key points. So the key points then go something like this. 1, the blue car's battery does not have enough juice, as they say, right? It doesn't have enough juice to turn on the car. It doesn't have enough push to force the required 100 to 200 amps through the blue car's starter. This is what turns on the car. 2, in a jump start, the blue car's starter is placed on the electric incline of the good orange battery. So once it's there, so then what you're seeing here is that now I have this situation. I have my incline, and so when I'm looking at this, this is telling me that now the good battery is setting up an incline. And then on here, you now come in and you put the starter, right? So this is in this situation here, you have the blue car's starter on this incline. And just like we talked about up here, there are charges already in the starter. So when I start to look at this thing, I already have charges in the starter. I already have charges on the incline. So as soon as I make the connection, by the way, in this situation, we're essentially saying something like this. This guy is 12.6 volts. And in this height, we would then say that this height here is 12.0 volts. So now that you have that, we could then say, we come to the same misconception that we did with the light bulb. Many people believe that charge squirts out the orange battery, travels through the jumper cables, and then starts charging up the blue battery. Right? Many people believe charge comes directly from the orange battery to the blue battery to charge it up. Not correct. If this was the case, a 2-meter jumper cable or cables would require a minimum time of 3 hours and 40 minutes. That's a long time. Just to begin charging the bad battery. I hope you have a snack. That's a long time to wait. We know that this is incorrect. We know that this is incorrect because many of the times the jump start immediately turns on the blue car. So that can't be true. That's the problem with the drift velocity. That's the physics behind it. So once again, so in summary, a different process must be occurring since the orange battery is able to start the blue car. It's because the orange battery electric incline immediately moves the charges in the blue car's starter. Now, that the blue car is on, the system starts the recharging process. And depending on how bad the battery is, you should let it, don't turn it off for a while.